Alright, so we know that we want to place our 0 right on top of our original pole 2. And so we know that we want omega z1 equal to omega p2. And what this means is we want 1 over our compensation capacitance times 1 over big GM2 minus our Z to equal big GM2 divided by CC. If we solve this for RZ, we'd find that we want RZ equal to our compensation capacitance plus the capacitance at node 2 divided by the compensation capacitance times 1 over GM2. If we multiply through, we find that we want 1 over RZ to equal 1 over GM2 times 1 plus C2 divided by CC. Now doing this also moves our third pole because our third pole is dependent upon the value of our Z. So remember, our third pole, omega p3, is equal to 1 over RZ times C1. And so substituting in for our value of RZ, we'd find our third pole frequency is equal to 1 over C1 times 1 plus C2 over CC divided by, or times 1 over big GM2. What we're doing now is we'd like to have a 45-degree phase margin. And what we're seeing here is that what we've done with our compensation capacitance and 0 is we have our first pole, omega p1, when we're drawing our Bode plot. We get a roll-off. Now we're causing a pole 0 cancellation at what our original second pole frequency was equal to, so that we get no net change, and ultimately our system comes to our third pole frequency, omega p3, where we now get our new roll-off. So here we have a minus 20 dB per decade roll-off. At the pole 0, nothing happens because the pole 0 cancellation occurs. And at our original third pole, we get our 40 dB per decade roll-off. And we know that if we want a 45-degree phase margin, we try and make our closed loop response intersect our open loop response at whatever the second pole frequency was, even if the second pole frequency is an effective pole frequency. And so our compensation capacitor, CC, is equal to big GM1 divided by omega p3 times whatever our desired closed loop response is. If we substitute everything in, we can find that our closed loop response, our compensation capacitor, is equal to square root of big GM1 over big GM2 times C1 times C2 over whatever our desired closed loop response is. Now remember, C2 is most likely dominated by the load capacitance, assuming that the device capacitance is fairly small. So this gives us a guide to how we would size the resistance that we'd like to see for our compensation. We know that the resistance we'd like to see for our compensation is given up here, and our desired compensation capacitor size can be given by the expression that we just derived. In class, we'll look at how to actually implement such a circuit.